More minutes to go.
Oftewel, de Antilliaanse Chopin speelde een wals uit een van zijn Antilliaanse dansen. Daarvoor hoorde je Camerata RCO met het vierde deel uit Mozart's klarinetquintet.
Met erop deze week Finse pracht van Jean Sibelius, zijn tweede symfonie en koning Christian. Uitgevoerd door Zweedse muzici van het Göteborgse Symfonieorkest onder leiding van Santu Matthias Ruvali. En met deze prachtige namen heb ik nog één naam in petto, namelijk de winnaar of winnares van vandaag. Ja, wie wist het? Wie wist in welke stad Sibelius destijds begonnen is met het componeren van die tweede symfonie? Het gaat hier om de Italiaanse stad Rapallo. En Rapallo, dat was ook de inzending van Evelien ten Kate uit Moordrecht. Evelien, gefeliciteerd met Moord.
Ja. Okay, it's 1:45. Welcome to the live stream on in the lectures on multibody dynamics. It's a bit strange. I'm sitting here in my room and there's no audience. It's not in a lecture room due to the coronavirus measurements. But luckily the whole course was already online and e-learning and everything. So we'll just continue as is. For me it's a bit strange talking just to my books in my room. So not very inspiring, but I'll do my best. For you who are used to be in the lecture room, it's also a bit strange to watch it in the live stream or afterwards in the recording. Well, anyway, we'll all do our best, and if we put our shoulders under it, we will succeed, I guess. Today's topic, so we're in lecture number 5. It's about generalized coordinates, where we use virtual power and D'Alembert forces, and instead of using a Lagrange equation, we have another method which is called the TMT method. The word is not by me, somebody else came up with that word. I always like to say it's virtual power and D'Alembert forces and generalized coordinates, but anyway, TMT method, it's a sort of a shorthand. It's chapter 14 in the book, and but before we start, of course, with the contents, we do the Kahoot quiz. I checked, and the latency is at least less than 10 seconds. You have enough time actually to you have enough time to follow to answer. The questions are timed, but the timing is okay. I'll make it such that it's visible for yeah. So okay, let's start with classic. I'm not going to maximize the screen, otherwise the thing will totally go wrong. Yeah, very good. I see players coming up. And if I remember well, on average, together with a lecture room, we had like 130 participants. I expect it will be a little bit less now, but let's see how it damps out. Okay, 120. I didn't know I had this. I didn't know this was my student ID, but it's interesting. Okay, let's start. 5 questions again. The missing word is and of course I should say please discuss, but well, there's nobody, and I guess most of you are sitting by themselves behind the computer, so there's little to discuss. Of course you can also look this up, right? If you have the book. Yeah, very good. Point de figure. It's a bit sounds like a bit archaic French. Of course, beaucoup is wrong. There are just no figures can be found in this book. Quelques is a few, and peu is little. Okay, next. Yeah. Lagrange has no figures in his momentual work because, well, why were there no figures? He didn't like drawing, or he was bad at it, or he uses geometrical and mechanical arguments, or his methods only use algebraic operations, or it was rather expensive to include drawings in the book, which also could be the case. Indeed, his methods only use algebraic operations. Very well. Okay, now we move on to a little more content. So this is about the potential energy of a spring, and the spring has some strange nonlinear behavior. And the question is, what would be the potential energy function for this spring? You have enough time, just do the math. And if you forgot about the definition of the potential energy, just look up in the book how it's defined and then solve the differential equation. Yeah, completely correct. If you take the differential with respect to the length, then you should get the force. Okay. The fourth question. This is about not having a unique solution. This is about the pendulum with the moving base. And if you closely look at the equations of motion, then something is going on when the angle is 0, or when the pendulum is hanging vertical. There are then actually no unique solutions. And the question is, how did that come? What is the reason for that? Of course, we all know that a non-unique solution has to do with the determinant. That apparently the determinant of the mass matrix is 0 for this case, where the angle is 0 and k pi. But the question is, what is the physics behind it? Why is there no solution? Yeah, that's so this is a take-home message, and I will talk a little bit at the end of the lecture also about this. So apparently the correct answer is that we have zero kinetic energy for non-zero generalized forces. Now, it's not so clear that that's the case here, and I will demonstrate it at the end of the second part of the lecture of today. The whole thing is that you can have a speed distribution, an s dot and an alpha dot, such that this thing is not moving. If this is moving forward and the other one is moving backwards, then the thing is stationary, but you have finite values for the velocities. But I will go into more detail on that. Okay, now the last question, which is really calculating some stuff. It's a point mass, which hits a fixed wall. And it's an impact, and the coefficient of restitution is 1/2. And the question is how much energy is lost due to the impact. You have 90 seconds to do this, so just do the calculation, take your definitions of impact, and determine the energy loss. Yeah, one of the problems, of course, is not that we're not in the room, is that we cannot discuss among each other. And that's a bit unfortunate. Yeah, again, this is a take-home message. Yeah, more than 50% were wrong in this case. Where the 6 Newton meters came from, I don't know. But anyway, the correct answer is 9 Newton meters. How does it go? Well, the calculation goes like this. We have an amount of kinetic energy before impact, which is half mv squared, which is 3 times 4 is 12 Newton meters. Then after the impact, by definition, with an e and half, and this initial velocity of 2, after the impact, the velocity is 1. And in the other direction, but that doesn't matter. And then the kinetic energy of 1 is like 3, so 12 minus 3 is 9 Newton meters. Okay, and that ends up the thing. On the podium we have a winner, 3rd place, 2nd place, 1st place. Yeah, that's very good. Okay, then I want to get some view the report, show the feedback. Yeah, please give feedback. That I like to give feedback. You have now feedback. I also like to give feedback. Okay, I'm going to save the results, do a direct download, and I'm also going to save it to the drive. Better be safe than sorry. Okay, that having done, we can close now the Kahoot quiz. Yeah, so we even can close this, and we go back to our lecture. Okay, let's get this out of the way. So again, today's topic: generalized coordinates and virtual power, TMT method, chapter 14 in the book. Yeah, we did have the Kahoot quiz, right? So I have to write that down. And then, okay, how do we start? Well, our starting point again is a virtual power. So we start again from virtual power. And the virtual power expression, where we just use the CM coordinates, is of course delta P, this strange delta, and it can be any symbol, but Fi, the applied forces. Then we have the mass term times the accelerations times the virtual velocities, and then that's for I and K is 1 until 3, and N is then the number of rigid bodies we have. Let me exemplify that the xi's are CM coordinates, so they are like x1, y1, phi1, etc. until xn, yn, and phi n. And then the applied forces are force in the x direction on body 1, force in the y, a torque on body 1, until we have a force in the x direction on body n, force in the y direction on body n, and a moment on body n. Then the missing term here, of course, is what is the mass matrix? Well, in general, that is a diagonal matrix, right? A diagonal matrix, and the entries we start with M1, that's the two Newton equations, and then I1, and that's the Euler equation, and that then continues until the nth body, Mn, In. Now let's look at our specific example, and I draw now the double pendulum to illustrate what we are doing. So fixed to the base, then here we have body 1 and here we have body 2. We have some coordinate system, right? X and Y, and maybe it's handy to hand in what the angle of rotation, the direction is, that it's counterclockwise is positive. Now we have in total, the number of coordinates is in our case 6, and we have 4 constraints, and meaning that we have only 2 degrees of freedom. And for those 2 degrees of freedom, we can choose a set of generalized coordinates. So, and that's a choice we make. We choose generalized coordinates, and in this case, my choice will be, and it's also up to you. You can also make another choice, but I like to use 2 angles. So the QJ is then 2 angles, and I take the absolute angle of body 1 with respect to the horizontal, and the absolute angle of body 2 with respect to the horizontal, the x-axis. So these 2 angles, alpha and beta. But as you like it, you can also take another choice. But for now, I like these 2 absolute ones. Our next step is that we now have to express our CM coordinates, which we also call xi, in our generalized coordinates, which we tend to use call qj. And the general expression for that is xi is some nonlinear mapping of qj. Now, the thing I wrote down, the ti, is very confusing. The t is not kinetic energy, so this is not kinetic energy. And I've contemplated a lot about using another symbol, but in time, the word t every time emerged. Why? Well, because it's the t from the word transformation. That's why we use the word t, transformation. So we better get used to it. If you see a t without an index, it's probably kinetic energy. If you see a t with an index, it's probably the transformation mapping. And in a minute we'll write this down in detail, but for now let's move on. So if we have our coordinates in our non-linear mapping, then for the velocities we can easily write the following. And the velocities x dot I are, well, first we have to differentiate with respect to our generalized coordinates, and then times our generalized coordinates, the time derivatives. And again, here I runs from 1 to 6, we have 6 CM coordinates, and j runs from 1 to 2. We only have 2 degrees of freedom. Well, the same holds actually for our virtual velocities. There is actually no change in that. The only thing we do is we put this magic symbol in front of it, the delta, but you could also use some other symbol. You can do an index v or whatever. Then finally we need in our equation of motion, let me go back, here we have the expression for the acceleration, so we need to express our accelerations in terms of our generalized coordinates, their speeds and their accelerations. So for the accelerations, we now can write, well, we just take this expression and differentiate again, so x double dot I keep the first part constant, and I first differentiate this with respect to time, and then the second part is a Ti Lm, and that's Q dot L, Q dot M. Well, the dot is not, so dot is clear now. These terms, this second one, we tend to call convective terms. They are quadratic in the speeds. And quadratic in the speeds meaning these have the form like alpha dot squared L or V relative times alpha dot. If you look at the dimensions, these are all the dimensions of a meter per second squared. This people recognize as centrifugal forces, and these are sometimes called what I call the Coriolis type of not force acceleration, of course, centrifugal accelerations, Coriolis type of accelerations. Okay. Now we have introduced new coordinates, extra coordinates, meaning that we also have like extra forces. So we have introduced extra coordinates, being these QJs, and then we also for free, then we also have extra forces, and I call them the generalized forces. Generalized forces. And I like to use the symbol capital QJ for that. Now, and how are they defined? They are defined by power, actually, defined by mechanical power. Or in other words, if I take the dot product of this guy with this guy, then the result should be mechanical power. Or in other words, power is this QJ, Q dot J. With summation, of course, over the J. How does that work? Well, and what is then the dimension of that force? Well, that all depends on what is the dimension of the generalized velocity. Let's assume for your QJ, that's not a Q, for your QJ, and then here we get power, and then here we get Q capital, the generalized force. Well, let's assume you use an angle alpha, which is radians, right? Well, then it's the velocity is becoming radians per second, and then we have to come up. The product has to be Newton meter, and a Newton meter per second, of course, and not power per unit time. We have radian per second, so apparently then the force is a Newton meter, so that's a torque. If as a generalized coordinate we would have a distance s in meters, then we have meter per second, So maybe better even to write like this. Then again, the product should be Newton meter per second, and then the result is, of course, then the force will be Newton. Now suppose you use some very strange type of coordinate. This looks rather simple. Suppose you take as a coordinate, you take some distance squared. So the unit of that one is then meter squared, right? Then what is then the unit of q dot? Well, you get 2s s dot, right? And so that's meter squared per second. Now we want this q times this meter squared per second must be Newton meter per second. Yeah? Ergo, this q is apparently Newton per meter. That's just how it works. So then you know, then my dimension of this generalized force, which is not really a force in that sense, is a Newton per meter. Well, I can continue hours like this, but the concept should be clear now. The generalized force is defined by having already defined a generalized coordinate. Let's move on. So let's go back to our virtual power expression, delta P. But now we have to extend it with our extra forces. So I put a star there. So we start again with our applied forces, with our D'Ampere inertia forces, and then times the virtual velocities in the CMs. But now we have to add to this our generalized forces and our virtual generalized speeds. And we say that should be 0 for all virtual velocities j actually, because those are the independent generalized velocities. These one are dependent, but these are the independent ones. So if these are for all non-zero generalized speeds, virtual speeds, this should hold. And then the conclusion is, then the system is in dynamic equilibrium. Or in other words, we get our equations of motion from that. Now if we look at the equation, this is already in the generalized coordinates, but now we have to recast this in terms of generalized coordinates. Well, the first part are the accelerations and the second part are the virtual velocities. So for the accelerations we use of course our expression here which we got, our general expression for our accelerations with our coordinate transformation. Don't tilt. So we get the accelerations are tk, j, q double dot j plus is it smart to use a j? Oh, that is okay. Plus tklm q dot l q dot m. That's one. And then for these virtual ones I write, well, first the real velocity is ti, j times the real velocity, and of course virtual, I just put this. So then we plug this in here and we plug this in over here, and then finally we get the following expression for our delta p star, the applied forces of course, then minus our mass matrix, but now we have to put in this stuff, tk, j, double dot j, plus tk, lm, q dot l, q dot m. Actually, in hindsight, let's change this index because I already want to use the j for something else. Oh. And let's use an L here. It's a dead index, the summation is over the index, so you can use anything. But I don't want to create any confusion with the j's I end up later. So I have this one, I close my bracket. Now I have to substitute for this expression, so I get my ti, j delta q dot j plus, and then I have my forces, my generalized forces, times these virtual one, and that should hold for all virtual velocities, as long as they're not zero. Well, then the conclusion is we get J equations of motion, right? And they are, well, you can have, because we now have everything in these virtual velocity expressions, the same one. So we get J equations, and I'm going to pull this in front. So I'm going to write Ti, comma J times Fi minus, then I'm going to expand these two, so I get Mik times Tk, comma L Q double dot L plus, and I get Mik. Now I can write this out, of course, the Tk Lm Q dot L Q dot M, but we will actually call this whole shebang, we will make a new symbol HK out of this, and we'll do that in a second. So now we close the bracket, we had this bracket and this bracket, and then the only thing which is missing is our capital Qj is 0. So these are our equations of motion. Well, it looks like a big mess now, but I introduce, to make it a bit convective, accelerations, and I call them HK, so HK equals, and then that's this stuff, Tk Lm Q dot L Q dot M. Because in the end, of course, the L and the M are just dead indices, the outcome is K, it's just accelerations. Okay, now we can reorder some stuff. We are used to mass matrix times acceleration is forces. So let's rewrite that then, meaning we pull out this first part. So we get Ti, comma J, Mik, Tk, comma L, and maybe I put a bracket around it to show that it's a one unity thing. So like a matrix equals. Well, let's start with a Qj. Well, here was a minus sign, so you could also say, well, I multiply everything with minus and then put it on the other side. Anyway, we have to keep track of the right signs, Qj. Then we have, for Qj, we also now add up this, and what does that mean? What is this? Well, this is the forces at the center of mass, which are transformed by the Jacobian. And they are added up to these generalized forces. So it is a way to transform our CM forces to our generalized force base, actually. Are we missing something? Yeah, this last part we are missing. So then I have to add, plus, and maybe we do it like this. And it's a D'Alembert force, so it's the Mik times Hk. And then we close the bracket. And those were all the terms, right? So let's put a box around it. And this is what we call the TMT method. Now it's super clear now why it's called TMT method, right? And maybe remember that this guy is this guy. Why is it called the TMT method? Well, we see here this matrix multiplication. We see the transformation matrix, we see the mass matrix, and we see the transformation matrix. So apparently the mass matrix is pre and post multiplied by this transformation matrix. And that is why we call it TMT method. Now, what we could do is we could make a like a sort of shorthand notation, like this mixed. Let's do it in a mixed vector matrix vector index notation. Matrix vector index notation. Just to clarify what everything is, and then the Tij, because it has two indices, I can say, oh, I call that a matrix with a Ti and j. So I is the row and j is the column. And likewise, well, Mij, two indices, I make a matrix out of that, again with the I and the j as row and column. So this is now a matrix, right? And this is also a matrix. Then I'm going to define some vectors. So if we have this Qj, then I'm going to make a vector Qj out of this. So this is a vector. And if I have my Fi, I'm going to make also a vector out of this. Okay, so now I have defined my stuff. Actually, I also have an Hk in which I make into a vector Hk, right? Having defined those, I now can write it in this sort of mixed mode. I get T transpose. Now why transpose? Well, keep a close watch. So the multiplication is, it should usually be that you take the row times this column, but now the rows and the columns are mixed. It's Ij times Ik. And here the K and the L, they comply, but here it's a J and the I, so it's the I and the I, then you have to exchange rows and columns. So that's one matrix times Q double dot equals the generalized force vector plus T transpose times the applied forces minus some convective terms. So this is in this TMT method, in this matrix vector notation. You can even simplify it more by saying, well, let's define a matrix M bar, and this is defined as T transpose times M times T. And let us define a force vector which is called Q bar, and that is a force Q plus T transpose times the force M minus M H. Then with this definition I can finally write my whole equation of motion as M bar times Q double dot equals Q bar. And that may look like a surprise, but of course it is not a surprise, because in the end everything is Newton and everything breaks down in the end to sum of the forces is mass times acceleration. Maybe I should write it the other way around. Forward. I should write sum mass times acceleration is sum of the forces. Of course, everything is Newton in that sense. And this is just to show that it's Newton. Only it's a bit more complex. The mass matrix is transformed and it's now coordinate dependent, as we will see. After the break we're going to make an example. The forces are a bit extended with convective terms, centrifugal acceleration and Coriolis type of things. And okay, so that is the TMT method. Then a smart mouse, of course, would say, yeah, but we already can do this. We can already transform our equations of motion in terms of generalized coordinates by means of the method of Lagrange. You wrote this wonderful book on that. And why do we need something extra? Now, bear with me. The thing is that with Lagrange, when you had very tiny little systems and did small analytical work, that was a nice way, but there is a disadvantage, because in the Lagrange method you first go up to the level of energy by integration, and then you go down again to the equations of motion by differentiation. So let me show how that works. So Lagrange, with Lagrange you started with sum of the forces is mass times acceleration, but then what did you do? You say, well, now I'm going to make energy out of it. So I'm going to multiply it with dx and I'm going to integrate it. And of course for the dx sometimes you also wrote x dot dt, which is identical of course. Anyway, by doing that, you come up to a level of kinetic and potential energy, and mind the confusion with transformation, but this is kinetic energy. So kinetic energy, and this is potential energy. Potential energy. I don't know why I have a thing here. Go away. So you go up to that level, and then to get the equation of motion, what do? Well, you have to differentiate again, and you have to differentiate in a very strange way. You first have to take the partial derivative of the kinetic energy with respect to the speeds, and then differentiate it with time, and then you have to subtract the kinetic energy with respect to the coordinates, and then you have to add up potential energy with respect to the generalized coordinates, and those are then the generalized forces. Or, in other words, the Lagrangian method. You start with Newton. Then you go up a level to energy. And how do you do that? By integration with respect to dx, right? Then at the energy level, you go down again by differentiation, and then you get your equation of motion. So you see the amount of extra work you do in the Lagrangian route. So this is actually the Lagrangian route. And what is the TMT route? Well, the TMT route is just you start with Newton, you take your transformations, you multiply by means of your transformations, and then in the end you have your equation of motion, and everything stays on the level of Newton. You don't go up to some energy and then go down again. There is no integration in play, there is no differentiation into play. Okay, so this summarizes the stuff I wanted to talk about in the first part. Since there's no audience, things go a little bit quicker than expected because there are no interruptions of questions, unfortunately. We could do that, but it sort of, well, it changes also the flow, and then people ring in and I cannot handle that. So I propose we do a break now, because after the break I want to do an example. So you can take coffee or tea, break, and then after the break, and we start again at really on the clock, because most people really are sitting somewhere else. So and that is, now I have to be correct, 14:45, right? That's when we start again. So take a cup of coffee, take a break, stretch your legs, and then after the break we're going to do an example. Okay, see you all in, 17 minutes.